We're glad that you could join us today. My name is Jessica Shipley. I'm an associate with RAP's U.S. program, and I'm pleased to welcome you to today's webinar on smart non-residential rate design. We're going to be sharing best practices for aligning rate design for industrial and commercial customers with the goals of reducing power system costs and providing benefits for all customers. We're recording today's session and we'll be sending you that link in the next day or so. And we're really looking forward to your questions, so please go ahead and type them into the questions pane on your GoToWebinar control panel, as we're going to show you on this slide. We will be pausing briefly during the presentation for clarifying questions, and we'll address all other questions during the Q&A session at the end of the presentation. So the official portion of the webinar is going to last 1 hour, but we want to answer as many of your questions as possible today, so we'll stay on the line for up to an additional 30 minutes for anyone who would like to continue the discussion. Now I'd like to introduce our speakers today. Dr. Carl Linvill leads our work on renewable energy integration and transmission planning in the Western U.S. In his past life, Carl was a Public Utilities Commissioner in Nevada and an economic and energy advisor to Nevada Governor Kenny Gwinn. His areas of expertise include power sector markets, procurement and planning, distributed generation valuation and tariffs, and regional reliability solutions. Jim Lazar has maintained a consulting practice in electric and natural gas utility rate making and resource planning for more than 35 years and has assisted RAP on projects in the U.S. and around the world since 1998. Jim has written extensively on rate design, renewable energy integration, consumer participation in electric utility planning, integrated resource planning, and incentive regulation. And with that, I'd like to turn it over to Carl and Jim.
Good day, everyone. This is Carl. So first of all, what we're going to be talking to you about today are large customers, large non-residential customers. We have in mind businesses like Safeways, like an office building. We don't have in mind very small commercial enterprises like Scratch Bakery. We don't have in mind large industrial processes like petroleum refineries or something of that sort. So we're going to be talking about rate design principles for those type of customers. Throughout this presentation, we're going to be talking a lot about demand charges, which is a very portion of the non-residential customer bill. It's going to be very important for you to keep in mind the difference between the non-coincident peak demand, that highest level of demand that a customer uses during the whole month, versus the coincident peak demand, which measures the customer's usage at a time of system peak. This difference is it's really important to keep in mind the difference as we go through this. So what our presentation today is going to focus on are a couple of problems and a couple of solutions. First of all, we're going to observe that most non-residential rate designs do not align customer rates with system costs. Secondly, we're going to observe that technological change and the emergency of distributed energy resources make this misalignment of rates with system costs an even bigger problem, and therefore improving non-residential rate design soon is very important. We're going to talk about a couple of solutions that apply most places in the country. First of all, non-coincident peak demand charges should be lower. Generally, they are too high, and they provide a distortionary price signal that we'll be talking to you about. Second of all, time of use rate design better reflects system costs than coincident peak demand charges. And so we'll be talking about how coincident peak demand charges really should be replaced with time varying rates such as time of use charges. So first to the first problem. Most non-residential rates don't align customer rates with system costs. So let's think about what a rate typically looks like, what a rate design typically looks like for a non-residential customer. There's a customer charge that's a fixed fee each month. It's about $100 a month in this example. There's a demand charge, and you see here we're not differentiating between non-coincident, coincident. We're just talking about demand charges. Most non-residential bills have both types, but for this simple example, we'll just talk about a $10 per kilowatt demand charge, and then an energy charge, which is a charge on the volume of energy consumed by the customer. So the big problem and the big issue that we want to drive home is that rate design should make the choices that the customer makes to minimize their own bill consistent with the choices they would make to minimize system costs. We want that alignment so that customers are making good choices in adopting technologies and in operating technologies in a way that benefits not only themselves through reducing their own bill, but also benefits the system as a whole. So what's the problem with this simple rate design we talked about? The customer charge of $100 a month, not much to talk about there. The demand charge, $10 a month. The problem with that demand charge is oftentimes it is a non-coincident peak demand charge, or a good portion of it is a non-coincident peak demand charge, and therefore it is not linked to system peak. And even if it is linked to system peak, maybe it's not done so in as refined a way as we would like to align customer choice with system benefits. And what about that energy charge? The problem with that energy charge is that it's not time differentiated, particularly in the world that we're operating in today, where there are more and more renewable resources on the grid, where there's more variation in the cost of energy over the day. It's important to convey these price signals to the customer so that the customer can align their choices to purchase when prices are cheap and to hold back from purchasing when prices are dear, if they can do that. The second problem that we have is that with technical change and the emergence of distributed energy resources, improving this rate design is really necessary right now. While the traditional principles that we have all been brought up in the rate design field from Bond-Bright are still useful, we really need to focus on some other basic principles. One of these principles with regard to Bond-Bright that perhaps we can talk about in the question time is the revenue adequacy issue for utilities. Because we are concerned that as we move away from demand charges, we still maintain revenue adequacy for the utility. But where we really want to keep our eye on the ball is to take advantage of what technologies make possible and necessary. The smart grid is making better rate designs possible. We have better information on what's going on the grid. We also have better information on what's going on at the customer's residence behind the meter. This better information allows us to come up with much more refined rate designs that do a better job of aligning customer price signals with system conditions. Distributed energy resources are being invested in large volumes by businesses today. We have businesses adding storage. We have them adding large solar arrays. We have them thinking about electric fleet vehicles. All of these additions by the customer can be of great benefit to the entire grid if they're used in a way where their use aligns with system need. If we don't fix rate design, we're going to be stuck in a situation where customers will adopt these great new technologies. They'll focus them on just reducing their own bills, and if those rate designs aren't well aligned with the system needs, minimizing their own bill will not align with minimizing system costs. So the rapid deployment and introduction of these great new technologies really requires that we get started with this revision of rate design now. This is not a new topic for RAP. We have, I'm sure you're familiar with the publication a couple of years ago on smart rate design for a smart future. This piece of work gave some simple principles on how technological change and the emergence of DERs are affecting residential rate design. And here are the three principles that we laid out in that paper. The paper did address non-residential customers to some degree, but more recently we were tasked with taking on this issue of non-residential rate design for the California Public Utility Commission. Last December we published a paper for their use in a proceeding considering changing non-residential rate design. This is the title page from that. And this rate design, this non-residential rate design paper enumerates a number of principles along the lines of those three principles. What we're going to be presenting to you today is kind of a boiling down of this more detailed paper onto a couple of specific solutions that we think you should focus on.
So this is Jim Lazar. The first of these solutions is that non-coincident peak demand charges should be lower. Most places recover the bulk of the distribution system cost in non-coincident peak demand charges. Now the costs that do vary with the customer's own peak are really limited to those costs very close to the point of delivery. The final line transformer, any secondary service lines to the customer do, in the case of large commercial, have to be sized to the individual customer. Most customers of this group we're talking about have dedicated transformers. And the cost to recover that, we think, belongs in what we'll call a site infrastructure charge. And that site infrastructure charge is most likely going to be measured in dollars per kW, but it's only going to be a couple of dollars per kW per month because it's not the whole distribution system, it's just that at the point of delivery. So for a small retail customer on a demand charge with 20 kW demand, $2 a kW, 40 bucks a month. For a supermarket, that becomes more like 600. For an office tower, perhaps 1,200, and a suburban shopping mall, perhaps $4,000 a month. That helps the utility recover the investment that has to be made to serve that customer's demand whenever it occurs, even if it's completely off-peak. So let's give an example of a couple of customers that are off-peak for most utilities. A school and a church. This happens to be a couple near my house. The church peaks on weekend days and has very light use during the rest of the week. The school peaks on weekday mornings and into the early afternoon, but by the time of the 4 to 8 p.m. system peak has reduced its usage considerably. A non-coincident demand charge would charge these customers for 45 kW each, even though their maximum combined use is 50 kW, and that's not at the time of the system peak. At the time of the peak, their combined use is only 20 kW. This is important. This is the issue of diversity, that these particular customers' demands are low during the system peak, and rate design needs to recognize that and price accordingly. Non-coincident peak demand charges really fail to reward load diversity. So we've said limit it to the site infrastructure, The shared generation and transmission and the shared distribution capacity cost should be reflected in time of use rates, generation, and transmission, certainly system-wide. For some very large utilities, perhaps there's a basis for more than one zone for distribution capacity pricing. The second solution is that time of use rate design better reflects system costs than even a coincident peak demand charge. So we're going to take a look at 3 actual large commercial customers. This is actual daily load of 3 customers on a utility that we've worked with. The red line is a big box store. The green line is a big box store that has solar on the roof, so you can see its load rising in the morning until about 7 o'clock and then declining sharply at the middle part of the day and rising again in the evening. And the third is an office tower. What's important here is to look at the system peak period and the sort of the 4 to 7 p.m. period for this utility. None of these customers peak at the time of the system peak, and that's not uncommon. The system peak occurs as the commercial load is beginning to drift down, the residential load is coming up, and they tend to intersect in the late afternoon. So there are a number of different kinds of rate design that do address the system peak demand. Well-designed time of use prices do that if the time of use period for the peak is narrowly defined. Critical peak pricing does that, where the utility gives the customer a notice of specific hours when the system is under stress and applies higher prices then. Peak time rebates, the flip side of a critical peak price, where the customer gets a credit for reducing usage during critical periods. Transparent real-time prices can do this. But the weakest tool for this that we've seen is the coincident peak demand charge. We've actually got quite a bit of research on the effect of time of use rate design. We published a paper in 2012 on time varying and dynamic pricing. We looked at over 100 different pricing pilots. The time of use pricing pilots produced a 5 to 10% peak load reduction. But if we added technology such as smart thermostats, building energy management systems, or automatic air conditioner load shedding controls, that went up to as high as 30%. The peak time rebate option produced 10 to 20% without technology enhancements and up to 30% with technology enhancements. And critical peak pricing produced 10 to 30% peak load reductions without technology and as much as a 50% peak load reduction with technology. So we know that these things work very, very well. Now let's take a look at what parts of the system costs vary with system time varying loads. And that's really the generation and bulk transmission part of the system. Power generated at these power stations can generally serve loads anywhere in the service territory of the utility or in a broader multi-utility area. Then there are some costs that vary with what we'll call Nodal TOU loads, the network transmission and distribution costs. That's everything from the point where the transmission system delivers into the utility's sub-transmission grid, the distribution substations, and in most cases the primary distribution circuits, unless a customer has a dedicated primary circuit, and a few very large customers do have that. These we think vary with the nodal loads on the system. For a utility that serves a relatively compact geographic area, there may only be one period that really covers this. But for those that cover a very broad area with more than one climate zone, there may be some parts of the system that peak at times other than the system peak. So I'm going to hand it back to Jess to see if we have any clarifying questions at this point of the presentation.
It does not look like we have any clarifying questions right now, Jim, so I think you can carry on.
All right, so we'll hand it off to Carl then.
Thanks, Jim. So the two solutions that Jim just talked about embody this principle or this idea that we stated initially, that the rate design should make choices that the customer makes to minimize their own bill, consistent with the choices that they would make to minimize the system costs. As we said at the beginning, this is very important as we move into adopting new technologies. Rates should promote beneficial adoption of distributed energy resources and beneficial operation of distributed energy resources. And when I use the word beneficial here, what I'm talking about is beneficial for all customers, not just the adopting customer. We know that a lot of investment is already happening in storage, in advanced controls, in electric vehicle fleet adoption, and so forth. And we think that the time of use rate with a critical peak price really does the best job of encouraging beneficial DER adoption and operation. This kind of rate design recognizes the system benefit of sharing infrastructure capacity, just like Jim's church and school example. If customers are using using system resources in a complementary way where they're not providing incremental impact, then that complementary use should be recognized. Time of use rate with a critical peak price is sending a price signal for all hours. The granularity of your time of use rate design can vary, but generally every hour of the year you're going to be communicating to the customer the price difference, and that gives a signal for how they should operate these technologies. The critical peak price provides an especially strong signal deterring high use in highest stress hours. This will encourage electrical vehicle charging during off-peak and shoulder hours, which is easy on the system and easy on the bill of the customer. It will encourage the use of air conditioning controls, ice storage, and batteries in a way that flexes use away from stress periods towards surplus periods, again benefiting both the customer and the system. So now we're going to present an illustrative rate design that promotes alignment. RAP, as part of the study that we did for the California PUC, we looked at about 20 different utilities, large utilities around the country, looked at their non-residential rate design. We looked at their customer charges, their demand charges, their volumetric rates, whether they had time of use rates and what they looked like, and we looked at their seasonal rates. And from that, we've brought you some examples to contrast how things are done in different places and to point you towards best practice. Jim?
So the first is what I'll call an antiquated rate design. This is a real utility in the U.S. It has a couple of $100 customer charge for large commercial customers, a non-coincident demand charge of $21 and change a kW, and a flat energy charge at a nickel. Obviously, the problems here, as we've described, is that the demand charge is based on NCP demand and the energy charge is not time differentiated. A better example is that of Georgia Power, their TOU GS10 rate. Same customer charge, but the demand charge is split into two parts. There's an on-peak demand charge that is much higher. That on-peak demand charge only applies to a 5-hour window in the summer. The rest of the hours, demand charge is much lower at $5.23. and it includes a fairly steep time of use energy rate. I will note this does not include any of the tariff adders for this utility, which may add significantly to the energy charges. But the best we found in our search around the country, and indeed in other parts of the world, because RAP does work in Europe and India and in China, was Sacramento Municipal Utility District, a site infrastructure charge of $3.80 kW per month based on the customer's highest demand whenever it occurs, a super peak demand charge, and then a both time differentiated and seasonally differentiated energy charge, reflecting the system generation, transmission, and distribution costs. We use that as the model for our modification. We really only made two changes in creating our illustrative rate design. One, we converted that super peak demand charge to a critical peak energy charge. And then we added a super off-peak rate because in many parts of the world, we're now finding hours when wind or solar are crowding the market, and we really want to give customers an incentive to shift flexible load into those hours. So here is that illustrative future non-residential rate design, a customer charge based on metering and billing costs, a site infrastructure charge based on the cost of carrying the investment right at the customer's point of delivery, and then a time differentiated rate for production, transmission, and distribution that adds up to a summer on-peak, a mid-peak, an off-peak, and a super off-peak rate. And then we've added to that a critical peak price of 75 cents a kilowatt hour during those relatively small number of system hours when the system is under great stress to get customers to take extraordinary measures. Now, if you're in a restructured state, we can simply blank out the generation transmission rates, and you can be looking at the form of the distribution rate, time differentiated, perhaps seasonally differentiated, and it may be appropriate to include a critical peak rate. I'll hand it back to Carl now.
So you might remember early on when Jim was talking about different time varying rates that could be beneficial, we talked about a dynamic and real-time price as a potential way of getting at that. We do like the dynamic and real-time pricing approach. It's just that many places in the country are not quite in a position to implement this today. So, and secondly, it requires more active management on the part of the customer. And some customers may not want to take that more active role, or may not want to hire an aggregator or a third party to take that active role for them. In that case, the simplified rate design on the previous page is helpful. But the really great thing about dynamic and real-time pricing is that it is conveying actual price information on the grid in real time. So it's an even more granular look on how you're affecting the system. So what we favor is to offer an optional dynamic real-time pricing option, and then move toward that becoming more prevalent over time as customers get used to it, and also as the infrastructure is in place to handle it. We're going to look at one quick case study here of how the three rates that Jim proposed affects EV adoption. In this table, you'll see the antiquated rate, the coincident peak demand charge rate that is roughly the Georgia Power example, and the smart rate proposal that we offered. The situation we want to think about is fleet vehicles or workplace charging for companies. Many places are trying to support companies that want to promote workplace charging or fleet vehicles. But some of these rate designs do more to help that than others. If we look at the antiquated rate, we find, first of all, charging a vehicle about 6.6 kilowatts, about 250 kilowatt hours. Assuming that, what happens under the antiquated rate? Well, it results in an average cost per kilowatt hour for charging your vehicle of about 38 cents. It's quite expensive. The Georgia Power-like rate, the coincident peak demand charge rate, comes in at about 12 cents. The smart rate comes in at about 10 cents. So if part of your public policy is to support businesses in adopting electric vehicles and encouraging electric vehicle use in workplaces and in adopting fleet vehicles, then really the smart rate and the coincident rate of Georgia Power do a much better job than one that's heavy with a non-coincident peak demand charge. Jess, I'll hand it to you.
Okay, great. Thank you, Carl and Jim, for that presentation. So we're now opening up the floor to your questions. So as a reminder, if you'd like to submit a question, please type it into the questions pane on your GoToWebinar platform. We do have some questions to get us started, so we'll jump into those now. I think this one, there's a kind of a category of questions that we have around time of use pricing and the relation to demand charges. So we'll start with that, and I think we have one that's sort of a clarifying question maybe. So Carl, I'll throw this one to you. What is the definition of coincident peak demand rates, and how are those different than time of use rates?
So a coincident peak demand charge is a charge that's assessed based on the amount that you use during a period that's identified as the system peak. Typically, those coincident peak periods would first of all, it would apply, it might be the highest use in the month, and it would cover perhaps a peak period of 4 to 6 hours. So unlike the time of use rate, which offers a different rate for every hour of the day, the coincident peak rate simply assesses your use based upon your usage during that coincident peak period. Jim, looks like you want to use this example to clarify.
Yeah. In its purest form, a coincident peak demand charge would bill you for your usage at the hour of the system maximum demand. But we don't know when that is in advance, and tariffs need to tell customers what the prices are at the time they're consuming the power. Retroactive pricing is generally not allowed. So what most utilities that have implemented a coincident peak demand charge have done is they've taken, in this case, a 3-hour period, 4 to 7 p.m. Monday through Friday in the summer months, and defined that as the coincident peak period, and each customer's maximum usage during that window determines their coincident peak demand charge for the month. Well, if you take 3 hours a day times 5 days a week is 20 times 4+ weeks a year, it's actually an 80-hour period that they're paying for their maximum use within that entire period. It's not really focused on the system peak the way a critical peak energy rate typically is focused on specific hours that are stressed for the system. That's the only clarification I wanted to offer.
Okay. This question is related to what you were just talking about. Do you think we should have demand charges at all, or should we go entirely to time-based volumetric charges? Maybe Jim first.
Well, we proposed a demand charge to apply based upon the site infrastructure that customers actually need to be sized to their own localized demand. Typically the final transformer or transformer bank and anything downstream from that, because those really do have to be sized, you know, for the church that has to be sized for Sunday, and for the school it needs to be sized for the morning when things are warming up. And everything upstream of that, the distribution circuits, the substations, the subtransmission, everything else is shared, and we think are more accurately, those costs are more accurately reflected through a time varying energy rate, so that customers who can share that upstream capacity pay for it in proportion to how much they use it, not in proportion to what their local maximum demand happens to be.
Okay, great. So you talked about how customers respond to price signals when you showed the various pilots. So these seem to work well when you can get customer adoption. So this question is asking, how have you studied how to get the best customer adoption rates of those types of rate designs?
Well, here we're talking about, you know, in this webinar, we're talking about supermarket and office building size loads, and not residential loads. And many utilities already require that those customers of that size be served on some kind of a time varying rate, and more are doing so. We think they're moving in the right direction for these very large customers. They certainly have enough money on the line and enough sophistication to invest in energy management systems, or hire outside aggregators to help them manage their energy into to minimize their own costs, and in so doing help minimize system costs.
I would just add that so in this paper we're really focusing on the price signal that's sent to the customer. So in the three different charging examples under those three different rates, we're focusing on delivering a price signal to that commercial customer where they see a price that's both reasonable from a system perspective. This is not a subsidy, it's a fair price, and it's a price that's really very beneficial for them to pursue that fleet vehicle or customer, or employee charging program. So there are other barriers to adoption of DER programs and electric vehicle adoption programs. What we're really focusing on in this webinar is just on getting the price signals right in the rate design.
Great, thanks. We have quite a few questions related to utilities and utilities' willingness to move forward with these types of rate designs. So here's one that asks, what about the pushback against bill predictability when transitioning from cost of service regulation to time of use pricing, regardless of aggregating services?
Well, first of all, we think this is cost of service pricing. Years ago, when we did cost of service studies, we divided costs into demand-related costs and energy-related costs. But as things like solar and wind and storage have come onto the system, which are, very capital-intensive costs that in a previous era we might have classified as demand-related, we now assign those to the time periods when they're actually providing service. Both the investment-related costs, or fixed costs, and the variable operating costs all get put into the time period when they're being used. The same thing with demand response. There's no investment at all. It's all expense, paying somebody to reduce their usage, and those costs need to be categorized into the relatively short time periods when those are used. So we think this is cost of service pricing. The second part of the question is the transition of customers. This is where Bond-Bright's principle of gradualism, I think, does come into play, that utilities may not want to immediately move all the way to an optimal rate design, but should begin that process, and along with it should be a customer education program. I've worked with one utility where the customer service staff actually met one-on-one with each customer that was going to face a significant bill change. And in many cases, we're able to help them figure out how to change their processes to finish up their most energy-intensive processes by 4 p.m. so that they stayed out of the super on-peak period with their largest loads. So there does need to be some hand-holding.
And from the, I would just add, from the utility perspective, this is quite a change. Many utilities have a very large non-coincident peak demand charge and gather a large amount of revenue from that charge. So it is very important to maintain a commitment to the financial health of the utility and the utility achieving revenue adequacy as we change to one that has far superior price signals. So we don't think that, and it's just not true, that you have to sacrifice price signals to ensure the financial health of the utility. You can have both. And what we attempted to provide here was a view to what price signals need to look like in order to induce adoption and operation behavior that's to the benefit of all customers on the system. But we do also acknowledge in those Bond-Bright principles, there is the revenue adequacy principle of ensuring that the utility is able to cover its costs. So the intent here is not to shortchange the utility. The intent here is to change where the utility revenues come from so that you get both price signals that convey true system costs and revenue adequacy on the part of the utility. Now, there are a few tools that have been used traditionally to help with this. Decoupling is one such tool. Another tool that's increasingly important at this time is performance-based rate making. Utilities are going to have investment opportunities related to upgrading and updating the distribution system and enabling these distributed energy resources. And they're going to be able to recover revenues on those things. And we think that commissions should consider performance-based rate-making mechanisms that establish some performance evaluation metrics, such as the rate of customer adoption of a beneficial technology, such as storage. Utility does a really good job at encouraging that through both its practices, now going beyond just the rates, but to its practices, encouraging that. Then we think that, you know, it's okay for some revenues to come from that. So the new basket of revenues for this utility in a new world may include some additional revenue sources, but certainly the principle of ensuring revenue adequacy persists. We just want better price signals while we attain that revenue adequacy.
I brought back the load diversity slide because the whole issue of cost of service pricing was raised, and our point is that the church and school, that between them never exceed 50 kW, should be able to pay a rate that reflects that they can share capacity on the system. If I put another customer in here, say a mini mart that's open 24 hours, you know, a typical gas station mini mart, that it also draws 50 kW. That customer can't share with anybody. They preempt that capacity at all hours. And this actually is something that the NARIC rate design group back in the 1950s addressed, and was addressed in Garfield and Lovejoy's text, Public Utility Economics, that customers who preempt capacity should pay more for that capacity than customers who only use it some of the time. And moving these costs into time-varying rates is one way to do that. Now, 50 years ago, we really didn't have the metering technology to do that. When I started my career, we had to actually manually transcribe data from chart recorders in order to bill a customer at a time of use rate. We did that for oil refineries, but certainly didn't try and do it for supermarkets. Today, that metering is very easy, and so it's very easy to give customers a cost-based rate in the form of a TOU price.
Okay, thanks. There are lots of other questions in that similar vein, but I'm going to switch gears slightly here. So this person says, most of the examples appear to deal with fully regulated markets. We have a lot of loads in deregulated markets where capacity, transmission, and energy are handled by a third-party supplier. Transmission and capacity are generally charged based on the grid's coincident peak. The energy charge has been declining as a percentage of the overall spend as energy prices are quite low. How do the principles that you're presenting here apply to states that have deregulated and where far less than half of the charge is not with the utility anymore?
And we addressed that during the presentation by blanking out the generation and transmission charges that in a restructured state would be set by someone other than the state regulator. And even there, we think that the distribution charges should again reflect the site infrastructure charge that is part of the distribution infrastructure. And then the distribution substations and distribution circuits and the sub-transmission that's below 230 kV, that's not FERC jurisdictional, should all be bundled into to the time varying rates because customers can share that capacity, and those who use it dominantly during on-peak periods should pay more towards those costs than those who use it during off-peak periods. But there shouldn't ever be complete hitchhiking on the system. Everyone should contribute something towards system costs, and the rate design that we described here for the restructured state, so we think accomplishes that.
Okay. So how does a commission vet the rates of its large commercial industrial customers and move toward these suggested reforms? Is in a rate case or a TOU rate application that emerges from say a smart meter implementation or some other way, and who should help with that vetting?
Harold, why don't you describe the California process that's now underway a little bit?
Jim, why don't you start with this one? I didn't quite get the question.
All right. Well, so California started their process with a workshop where they brought in experts, including RAP, to address the issues. I would describe there being almost uniform agreement among the experts at that workshop that non-coincident peak demand rate designs were a relatively poor rate form. Once we got past that, there was a broader spectrum of opinion as to what was right, ranging from academic theorists who thought everything should be reflected at the time of the system peak to more pragmatic, what I'll call more pragmatic practitioners who think that everybody should contribute something no matter when they're using the system. So that workshop was sort of one phase. The commission will be issuing some guidelines, and then we'll be addressing it in the individual rate cases of the individual utilities as they come up.
So Jess, did that, if you didn't, I'm not sure that answered the person's question as I heard it, but if it did, then let's move on. But if it didn't, could you restate the question?
It seemed pretty good to me, but the questioner can submit a follow-up if they want. But there are several other ones related to kind of implementation. So there's one here that says, how would a public utility commission determine the site infrastructure charges tailored for different types of customers? Jim, do you want to start with that, or?
Yeah, I mean, the cost, a typical embedded cost of service study, and for that matter, a marginal cost of service study, does price the final line transformer and the secondaries as a separate cost category. And what we're really saying is let's excise those out of the cost of service study and treat those as site infrastructure costs and figure out what they need to be. For the large commercial customers where there are pretty much always dedicated transformers, where their demand is measured in hundreds of kW, supermarkets and shopping centers, office towers, that's really quite easy to do. When you get into the residential sector or the very small commercial sector where there can be half a dozen customers served by a single transformer, or secondary networks where more than one transformer are serving a group of customers, it gets a little more complicated. That is usually a smaller commercial customer area. And then when you get to the residential sector, it ranges from rural customers who have standalone transformers and they'd pay the whole 15 or 20 kW worth of cost, to apartment customers where you may have 50 or 100 customers sharing a transformer or a 2 or 3 transformer bank that should divide it among all of their collective demands. So it's a little more complicated for the small customers. For the big customers, I think it's really quite simple.
Okay. So here's another one related to commissions. Can you characterize the willingness of commissions to seriously consider such smart non-residential rate design, especially when many utilities seem to be successfully pushing to go in the other way, or for various reasons?
So, I think that the Utility Commission, in terms of addressing the utility's concern, I think the utility's primary concern is that the loss of the non-coincident peak demand charge or these demand charges in general are going to result in a shortfall of revenues. And so I think the Commission needs to acknowledge that concern and needs to identify a strategy for addressing the concern. As I said, if you don't have some kind of decoupling mechanism, then the Commission should be taking that on. If you recognize that the utility's future investment opportunities are affected by this, and it's really asking the utility to take on a new posture relative to customers, to be more of a facilitator of relationship between customers and third parties, then you need to recognize that changing to that business model is going to require some transition on the part of the utilities, and there are ways of compensating that. So RAP recently completed a survey of performance-based regulation examples in, I believe, 17 different places with the National Renewable Energy Lab. I recommend that to you. Other folks at Energy Innovation have been working on performance-based rate making approaches. I would, this is not easy, but it's necessary. And utilities need to sense the willingness to address the full implications of the change, and the Commission needs to take that on and address it seriously. And then I think if that's done, then I think there are examples of utilities who have warmed to more granular time-based rates because they see it as consistent with serving the customer in this new environment.
Okay, great, thanks. I know we're getting short on time. I just want to ask one more question here. So you touched on dynamic real-time prices briefly, and it sounds like those send more timely information on system conditions. So why not use those instead of time of use prices? Carl, do you want to take that one since you're already unmuted?
Yeah, sure. Just so we're about out of time, so just real quickly, and we can talk about this more when we go to the bonus half hour in a minute. But yeah, main, there many places do not have the information infrastructure set up to handle real dynamic pricing at this point in time. Getting dynamic pricing down into the distribution system, at the substation level or feeder level, yeah, that will send much more granular price signals. But the utility needs to produce that information. That information needs to be available to customers, and customers have to learn how to use that information. So as Jim said earlier, some amount of gradualism is in order here. While utilities learn to operate in this new environment, and while customers learn to manage their usage in a more refined way with a whole new set of technologies available to them.
The illustrative rate design that we've developed does have a critical peak price built into it for you set a maximum 50 hours per year. That could be 25 2-hour critical periods or 10 5-hour critical periods. But during those critical periods, we are in effect sending some pretty dynamic information to customers and asking them to take steps during the hours that are most critical to system planning, design, construction, and reliability. So even our default illustrative rate has some dynamic elements to it, and getting customers actually all the way to an hourly price at this point, we think should be an opt-in choice even for these very large customers.
Okay, great. Thanks, Carl and Jim. So we do have several more questions to answer, so we'll go ahead and stay on the line for an additional 30 minutes, but I'd like to turn it back to you guys to leave us with your closing thoughts.
Yeah, so as we have said and repeated, rate design should make the choices the customer makes to minimize their own bill consistent with the choices they would make to minimize system costs. Current rate designs for non-commercial customers normally do not make this connection. So what we identified were a couple of problems. Traditional rate design does not align customer rates with system costs, and the fact that technological change like metering is available, and the fact that many commercial entities are investing in advanced technologies, storage, distributed generation, and so forth, we would like those technologies to be deployed in a way that helps the system. So we offered two solutions. A non-coincident peak demand charge should be lowered and replaced with other things. And number two, that time of use rate design should be implemented because it better reflects system costs relative to coincident peak demand charges. And we'll just conclude today with a reminder of the rate design that we offered. There you go. So thank you all very much for attending, and we'll be on the line for more questions in a moment. Thanks.
Yep, thanks Carl and Jim. So this, as Carl just said, concludes the official portion of the webinar, and we thank you all so much for choosing to spend some of your time with us today. For those of you who would like to stay on, we will dive back into some of the questions that we received, and if you still would like to submit them, that still is open, so feel free. Okay, let's see. There are a few more questions regarding utilities and their implementation of a smart rate design. So here's one that says, to enable a smart rate model, what and how prevalent are the challenges in metering and billing inside utilities?
For very large customers, I think they're pretty minimal. Even utilities that have not rolled out smart meters or advanced metering infrastructure to their residential customers have installed advanced meters at the sites of their very large customers. And even a manual meter reader who's going property to property can do what we call probe the meter, actually connect their data terminal to the meter and download the interval data from the meter. So I suspect there would be very few customers in the size range that we're talking about for whom there would be any additional costs to install equipment. There might be a need to update the software of the billing engine for these customers, but I don't think much of anything out in the field would be needed.
Okay, here's another question that says, utilities often argue that they must allocate to partial standby customers 100% of the utility's distribution or delivery system costs and build that into their demand charges or reservation fees. Is that fair? And how would you recommend that they allocate distribution costs?
We've actually published a number of things on standby rates. They're not in the resources that we're displaying now, but if you go to our Knowledge Center and search for standby, you'll find the stuff that we've done. The second publication on this list has some of that, and we've actually, in many cases, recommended daily demand charges for, for example, for combined heat and power customers who occasionally take their systems offline. On a large system, if you can schedule customers to not do their scheduled maintenance at the same time, you expect them not all to have unscheduled outages at the same time, and it becomes a probabilistic study of how much additional capacity do you need. Now, when you get down to the site infrastructure, that does have to be sized to the capacity of the standby customer. And so we've included that in. But if a standby customer is able to schedule their maintenance into the off-peak hours, we think they should contribute something to the system, but it should be less than a customer that is drawing power from the system during on-peak hours when the grid is under stress. And the time of use rate provides that. So the customer is contributing to the distribution system, and they're contributing in proportion to how much they use and when they use it.
Okay, related to that, maybe this one for Carl. In these smart rates, do commercial customers, if they can't shift load, do they then become penalized for using more energy during times when they need to use that energy, especially when they're used to paying a fixed price?
Well, I don't know about penalized. The rates that are offered are matched with the effect on the system. Now, maybe what the questioner is getting at is, do all commercial customers, all non-residential customers, do they all experience lower bills under this, or are there some commercial customers that will experience higher bills and some that will experience lower bills? I would say that, yes, it will affect the bills that different customers pay. However, customers can control that through adopting technologies that help them to the extent that can be helped. To the extent that they have a technology that is inflexible, that it has to operate continuously, that they can't control, then yes, they're going to end up operating that system sometimes when the system is at stress, and they'll be paying more for the privilege of doing that. I don't know, Jim, do you have anything to add?
Yeah, I've got a couple of things to add. First of all, I've put up our each commercial customer is different slide again. With a non-coincident demand charge, the office tower, the blue line, will have an incentive to install batteries to reduce their use between 8 a.m. and 3 p.m. That will minimize their bill, but it won't do anything at all for system costs. Similarly, the big box store, the red line, would have an incentive to install batteries to reduce their demand at 2 p.m. But that's not going to do anything for the system peak demand. And finally, the solar customer is going to have an incentive to install batteries to minimize their use at 8 or 9 p.m. And that's not a good use of anybody's money. So, you know, moving it all into a time of use rate gives everybody an incentive to control their use most aggressively during the hours that matter to the system. And that will wind up being a fairer allocation of cost responsibility. But I did mention earlier that some hand-holding at the point of transition in any rate design is important. And utilities that I've worked with that have made this kind of a transition did have, because these are pretty large customers with big bills, and you know, they're tens of thousands of dollars a month in electric bills, sending out the key accounts specialists to meet one-on-one with the customers. In one case, we had a industrial process customer that figured out that they could complete their most energy-intensive work by the time the 4 p.m. On-peak period kicked in. Their maximum demand remained the same because they had the same giant piece of equipment running, but they made sure they got that machine done with for the day by the time the system peak hour kicked in. It was a relatively easy adjustment for them. Another industrial customer I worked with, a small industrial customer that would fit into this category, was a forging company that did metal machining, and they had been in the habit of doing melting in the morning and then machining in the afternoon, and they changed their process to do their melting in the morning. That was do the melting at an hour that was off peak for the utility, because that was their most energy intensive process. They just shifted, that was a morning peaky utility, they shifted the melting to the afternoon and then came in the next morning and did the machining. So customers can make changes, but it's important to work with them, make sure they know what is coming, and help them understand their choices of what they can do.
Great. So here's a question that says, how should we incorporate time-varying distribution cost price signals if they conflict with the system time of use peak?
Well, I think there's two answers to that. One is only do it if it's really important. That, in my opinion, simpler rate designs are generally better. But there are systems that have geographic differentiation in their system. Here I've got a slide of the service territory of Pacific Gas and Electric. It's about half of the state of California. There's really three different zones here. There's a coastal zone that tends to peak in the middle of the business day. There's an inland zone that is more driven by air conditioning. It peaks a little bit later in the summer day. And then up in the Sierras, there's mountain zone, which tend to be morning peaking in the winter months. And so for a system this large, having some regional or nodal time varying distribution rates can make a lot of sense. But if there's nothing intuitive to the customer about why they're being treated different, it's, I'm on, one circuit over from my neighbor, connected to the same substation and paying different nodal rates, would probably be difficult to understand, difficult to administer, and frankly difficult to calculate.
So I would just add that once when the information is available to convey these more granular price signals on the distribution system, then we can look at more complicated rate designs that recognize some of those differences. I think in the near term, something that we might want to consider is if there is an area of system stress on the distribution system that is not coincident with the system peak, and it's a special impact that's going to incur local distribution expense. It's going to require the distribution utility to upgrade a substation or reconductor lines or something of that nature. Then we can address that with a bill credit approach, where customers who come forward in that area with a committed plan that is verifiable to modify their behavior to relieve stress in that area could be eligible for a bill credit. So there are ways of getting at local congestion in addressing it, but it is over time, really what it will require is more granular, better information, and customers getting used to being able to manage that information.
I will say there's one aspect of our illustrative rate design that actually addresses this very well, and that's the critical peak pricing element. It is possible, because critical peak prices are typically conveyed to customers by text or email, or in the case of very large customers, perhaps by a telephone call, or by advanced equipment of the customer premises that will automatically reduce some demands, lighting or cooling, for example, when they get a critical peak price signal from the utility. Applying our critical peak pricing on a circuit by circuit or node by node basis is something that I think probably can be done by many utilities with technology they have in place today, and can be responded to by many office buildings with their building energy management systems, or supermarkets by controlling their lighting and chilling load to take load off the system for short periods of time. So we really do have a way within this rate design of addressing the distribution circuit that has a peak at a different time. And that critical peak signal, if it's applied on one distribution circuit and not on another, may encourage Safeway to install batteries at one store but not at another, to carry it through a short period that occasionally pops up. So I think we actually handle this problem in the default rate design, and in offering the customer the option of a true dynamic price, real-time price. Those could also be tailored to locations.
So a couple more questions about the illustrative rate design itself. Here's one that says, what's the chance, or what's the likelihood that the coincident peak period could shift as a result of the coincident demand charges? For example, a situation where a utility needs to frequently adjust this period in the rate design.
Well, it can shift. It has shifted on many utilities. California's defined on-peak as noon to 6 in the past. They're now advancing that later into the day because the noon to 4 period is being well served with solar today, both distributed solar and utility scale solar. Hawaiian Electric has adopted a time of use rate that has the lowest price in the middle of the day, something that we haven't seen yet on the mainland, but has been proposed by the California ISO, at least for the spring months in California. The system peaks will shift in response to changes in technology. They have shifted in the past as air conditioning became more prevalent in the residential sector. Peak demand shifted to later in the day. I guess my own opinion is that rate design should be stable for a period of years because people are likely to invest in both technology and behavioral change to adapt to it. But the world in the future will be different from the world today, and we certainly need to be anticipating that and expecting it.
In the paper that we prepared for the CPUC, we offered a couple of principles toward the end of the paper, one of which was that we recommend that rate design be considered on a more frequent basis. Rate design changes in rate design have been very infrequent in the past. So we recommend considering, as time periods change, that should be evaluated on a more frequent basis. As Jim said, some gradualism so that people can make investments and have some certainty about the next few years is important, but taking into account that changes in distributed energy resource technologies, changes in how the grid is operating are going to require commissions to look at rate design and rate design parameters on a more frequent basis than they have in the past.
Okay, maybe Carl, for you, could you comment on how community choice aggregators can participate in DER advancement for C&I customers and how you see entry of CCAs potentially allowing for a more granular geographic-based rate?
Well, community choice aggregators will be choosing their rate design. So for a footprint of a community, and this is actually a national webinar, so I should just briefly say what community choice aggregation is. Community choice aggregation, it's kind of a form of retail choice, but where the opt-out, or in this case, it's an opt-out possibility in California, for example, is a local community might establish a local retail provider to serve the customers within its footprint, and so they would then and they would take on ensuring the supply of energy for that local area. Now the utility continues to offer the distribution service, so the time differentiated distribution service is still something that's beneficial from the utility. But from the community choice aggregator, yes, there is the opportunity to further refine local price signals within the footprint of the community choice aggregator, because basically they have the ability to implement their own rate design, and so it can be tailored to the local community's needs. And if the local community wants to promote distributed energy resources at a rate that is more accelerated than what state policy requires, then the community does have the option of integrating that policy into the rate design that they choose to reward people for adopting, let's say, low carbon technologies, and to support deployment of infrastructure such as vehicle charging infrastructure in a way that meets local community goals. So yeah, it does seem to me that community choice aggregators do have the ability to tailor their local rate design and their local policies to match what their local community wants to select as goals.
Okay, great, thanks. I think we maybe have time for a couple more questions here. How would accurate valuation of ancillary system services affect the role of commercial and industrial customers?
Well, commercial industrial customers have the option. We didn't, so this presentation was about rate design for the commodity service from the utility to the customer. As customers have the ability to offer other services to the grid, whether it be to the distribution system operator or to the bulk electric system operator, such as an ISO, then they may want to avail themselves of that opportunity. So our presentation didn't directly address these other services. Let's say a fast frequency response service. Perhaps a commercial customer has the ability to offer that service into the market and be compensated for that. They can still do that. They just have to comply with the terms of the tariff in terms of, you know, how they operate that. But yes, there are other revenue opportunities for commercial and non-residential customers and for all customers to sell services in the grid that are kind of another layer of exchange between utilities, ISOs, and the customer.
Okay, here's one, back to some specifics on the rate design. Does it make sense to do a multi-part rate, such as a peak time rebate, customer DER controlled by the utility, and a coincident demand charge as a means to remain flexible and reward different types of resources? Or worded another way, is this smart rate leaving something on the table by not allowing DERs to be aggregated and bid into electric markets? Jim, do you want to try that one?
Well, I think we've actually addressed a lot of that with the critical peak pricing element. Customers could make those loads directly controllable by the utility in order to avoid critical peak prices, or they could program their own on-site energy management systems, in the case of these larger customers, to automatically respond to a critical peak price signal from the utility. But the question about whether a coincident peak demand charge, say one that applies to your highest use during a 100-hour window, is superior to this of basically spreading that over the entire on-peak period, so that there's an incentive to reduce load throughout the on-peak period. I think that the time varying consumption rate more accurately tracks costs and allows customers who can share capacity to also share the cost of that capacity, whereas a demand charge denies them the ability to share the costs of shared capacity.
And I would just add that I think the situation that is described in the question, the aggregation of commercial resources and the use and marketing and service of those, this is kind of like the community choice aggregation question, where, you know, there's still the distribution charge from the utility, and distribution rate design. What we see up here in the third column over to the right, that distribution design. In terms of you know, getting the energy delivery and meeting the obligations of the system, such as something like a resource capacity obligation to the system, in that environment, you can have the time of use distribution rate, but then you can have the aggregator providing service to the commercial customer in a way that is very flexible. So I think if I understood the questioner right, I think they're contemplating a retail choice kind of environment where an aggregator can represent them in planning for and meeting their requirements, as well as marketing the services that can come from their resources. This rate design for the restructured state doesn't preclude that.
Okay, great. I think we maybe have time for two more. You touched on this already a little bit, but we have a question about how commercial rate design needs to differ from residential rate design. Is there anything that you would elaborate further on that?
Well, maybe the key place is that the site infrastructure charge for large commercial customers will normally be dedicated infrastructure at each point of delivery, whereas in residential and very small commercial, you have multiple customers sharing. My house shares a transformer with 6 houses near me, and my small office shares a transformer with the other 32 offices in my office building. So that's one difference between the very large customers that we've been talking about here, supermarkets, office buildings, big box stores, that the site infrastructure tends to be dedicated. The other is that the metering and billing costs will be lower for smaller customers. The $100 charge that we show here for a supermarket is more like $5 for a residential customer for metering and billing costs. And we see that in the rate design of most utilities today, a much lower monthly fixed charge for residential, and in many cases lower still for multifamily residential, where even if you're reading meters manually, the meter reader reads 20 or 30 or 40 meters in a minute or two, instead of spending 5 minutes walking from house to house. So those are the two places that would be different. The rest of the shape of the rate design would be identical. And in fact, in Smart Rate Design for a Smart Future, we have a table showing rate design for essentially all classes of customers, and they all have the same basic rate form. But the differences are customers served at primary and transmission voltages pay less, both because they're using less utility equipment, but also because they're bearing the transformation losses. And we didn't get into the sophistication of primary versus secondary service rates in today's webinar, but we do address that. I think it's on page 54 of Smart Rate Design for a Smart Future.
Okay, great. Well, I think that is about all of the time we have today. We're sorry we didn't quite get to all of your questions, but we will do our best to follow up with those of you that we didn't get to afterwards. A recording of this webinar along with the presentation is going to be available on RAP's website, and as we said earlier, we'll send it to you by email. When you leave the webinar, you'll see a quick 3-question survey. We'd really appreciate it if you could give us some brief feedback. And with that, I'd like to thank everyone so much for spending time with us this afternoon. And thank you, Carl and Jim.
Hey, everyone.